Today I'll be showing you how to implement FIR filters on real-time embedded systems such as this little brain board I have over here, which is featured in the past few videos on STM32 firmwares. And you can see I've got a little program running on here, which is just reading the inertial measurement unit accelerometer and performing some filtering. So if I rotate about here, you can see the green signal is filtered, the red signal is the raw data, and I'd like to show you in this video how to come up with your own FIR filters, why we use them, how to implement them, how to design them, and so on. So let's get started. If you'd like to order these little brain boards for yourself to play around with FIR filters or interfacing with STM32 and sensors and so on, you can do that if you go to my GitHub repository, github.com/pms67, and if you find the little brain STM32F4 sensor board, I've actually put all the Gerber and assembly files in here, ready to order at JLCPCB. So you can just download those, go to JLCPCB, click quote now. If you upload the Gerber and the assembly file, you can get them shipped right to you, which is pretty cool. In a previous video, I go into more detail of how to do that, but just to keep it short, if you just go to my GitHub, download the files, and you can just order them at JLCPCB. All right, let's go on with the video. Today, I'd like to go through the design and implementation of digital filters, FIR filters in particular. We'll cover four main topics. We'll look at digital filters, what they are, why we need them, and where to use them. Secondly, we'll look at a specific type of digital filter, known as an FIR filter, and kind of look at the theory behind it. Then I'd also like to go through how we actually design one of these filters, with what's known as the Window-Sinc method. And lastly, we're actually going to be doing something really cool and implementing one of these FIR filters in real time. We're going to design one and then put it on an embedded system with an STM32 microcontroller and how we can actually filter real-world live data. Digital filters are a huge part of DSP, that is digital signal processing, possibly even the biggest part. We typically use them if we want to separate signals or restore signals. So for example, here we have a signal that has some underlying trend, but it's covered in unwanted high-frequency noise. The way we would typically suppress that noise or get rid of that noise is via a filter. A filter typically has one input and one output and does something in between. Ideally then our output signal on the right here will have the underlying trend of the original signal, but removed some of or if all of the high-frequency noise we had in the original. Now of course this is just one very simple use case of a digital filter. There are many more. The input signal to a digital filter is typically represented in discrete time by a sequence of numbers. And you can kind of imagine this as an array. And we typically denote that by the letter X. Now the signal samples are also spaced equally in time because we are using something which is called a fixed sampling frequency, denoted by F sub S. So we're sampling, for example, every second or every tenth of a second. And we typically note this in hertz. So 10 hertz, 100 hertz, and megahertz. Essentially, you can imagine this picture here. We have a magnitude and we have a sample number, and every fixed time interval, we look at one point. And those are our samples. And that's our input signal in discrete time. Once we have our input signal, or our array, we can then pass that through a filter that has a certain desired frequency response. Now the frequency response is there to essentially maybe remove high frequency noise, remove a DC offset, add some more EQ, for example, to an audio signal, and so on. There are many different types of filters you could use. And the nice thing is we can actually design this frequency response. We can choose what this filter's frequency response is. And a plot of a frequency response is shown here. We have magnitude on this axis and frequency on this axis. As you can see here, this is a typical low-pass filter. Low frequency are passed because we have a magnitude of 1, but as soon as we go up in frequency, the magnitude drops and the filter will actually not pass those higher frequencies. So this is a low-pass filter. Now because we are working in discrete time with sampled signals, we'll have problems with what is called the Nyquist frequency limit. And that's the sampling rate over 2. So we can effectively only design filters within this frequency range, from 0 Hz to fs over 2 Hz. Once we've passed the input signal through the filter, the output signal is then, of course, another discrete sequence of numbers, and we typically denote that by Y, which again you can think of as an array. And for real-time applications, the output signal or sequence will typically be the same length as the input sequence. Now there are, of course, many different types of filters that will not do that, for example, decimation filters. But in general, we will be looking at filters that produce the same output length as the input. The output signal will also have different characteristics to the input signal. This could be altered frequency responses, but also altered time domain characteristics. Now, for example, said before, you might want to use this filter to remove high frequency noise, remove a DC offset, or just cut out a certain range of frequencies, or amplify a certain range of frequencies. The question now is, how do we actually design a filter like this? One type of digital filter, and a very common one, is known as the FIR filter. And FIR stands for Finite Impulse Response. A filter in general will have some sort of input, denoted by X. We pass it through, in this case, an FIR filter, and we get an output Y. If the input sequence is a 1 followed by all zeros, then what we get out is known as the impulse response, right? We put an impulse in here, and we measure the output. And for an FIR filter, the output will eventually return back to 0. The filter is always stable. And you can see this in this picture here. On the left, we have the input sequence, a 1 followed by all zeros, and the output sequence for this particular filter might look something like this. So it'll eventually go back to 0. And this is why this filter is called Finite Impulse Response. As usual, the FIR filters will be defined by a sequence of numbers of finite length. So again, we have an array, typically denoted by H, which is a discrete set of numbers. And this is what is known as impulse response. And for a linear FIR filter, this is all we need to know about the filter to know everything about it. We know the frequency response characteristics, we know the time response characteristics, and so on. Now, to actually get the output of this filter, we need the impulse response, and we need the input signal. And then we do something which is called convolution. So the output is the input signal convolved with the impulse response. Mathematically, convolution is written like this. So the input signal is X, the impulse response is H, and we typically use this star, which is known as the convolution operator. Now, because we'll be working in discrete time, because we want to implement this on a computer, this convolution actually turns out to be this sum over here. Now, don't worry if you don't understand this or this looks a bit alien to you. I'll show you later when we're actually implementing the software how to do this. But this is a really, really useful and important formula which we'll be using for the software implementation. But this is how we get the output. The output is Y, the impulse response is H, and the input is X. The question now is, how does the impulse response of this filter determine the frequency of the response of the filter? There are two really important results which I'll leave unproven, but I'll tell you about them now. Firstly, the Fourier transform of the impulse response of the filter is actually equal to the frequency response of the filter. And secondly, we are convolving in the time domain from the formula we saw earlier, and that is actually equivalent to multiplying in the frequency domain. So we have a certain frequency characteristics for the input signal, we have a certain frequency characteristic for the filter, we multiply them in the frequency domain, and that is the same thing as convolving the time domain to get the output. So, quite simply, to design a filter, we need to come up with a desired frequency response. So this could be a low pass, high pass, or any arbitrary form of the frequency domain response. And then we just take the inverse Fourier transform to get the impulse response. In particular, I'm going to show you how to do this using one of the most common methods, and this is called the Window-Sinc method. Now, be warned, there's quite a lot of maths in here, so if you're not comfortable with it or you're not interested, feel free to just skip ahead to the software implementation, which I think is probably the most interesting part. So let's look at a simple low-pass filter, which has this frequency response in the frequency domain. So we have magnitude on this axis and frequency on this axis, and we want to pass frequencies below a certain cutoff frequency, known as FC, with a magnitude of 1, and above that cutoff frequency, we don't want to pass any frequencies. And this is a or the ideal low-pass filter. Now, as I said before, we need to take the inverse Fourier transform to get the impulse response. The integral in continuous time is this one here, and then we just plug in all the values. Remember, we're only integrating from minus FC to plus FC because all the other values outside that range are 0, and then we just do the integral. Now, it happens to be that if we solve that integral, the impulse response in continuous time, remember, is sine divided by pi t. And this is actually known as the sinc function. So here you can actually see where part of the name comes from for this method. Now the sinc function, if we plot it or do a little sketch, it's this one here. Unfortunately, this brings quite a few problems with it. Here again is the theoretical response, the impulse response of our low-pass filter. Now we can see several problems. One of them, it's non-causal. So for time values below 0, we actually have non-zero impulse response values, and we can't implement that. We also have infinite length. So even though these tails decay towards 0 as t goes to plus minus infinity, they will still be non-zero, so it has infinite length. And thirdly, because we want to implement this on a computer, it's in continuous time, and we need discrete time. But, of course, we have a solution for all of these. The first one is to shift the response to the right. Then we want to truncate, we want to chop the left and right ends off, and then we want to discretize. So we want to sample this function at fixed periods. Now, once we do that, we can actually come up with this realistic response over here. As you can see, we shifted the impulse response, we've truncated the ends left and right, and then we've sampled it, which is shown by these bars here. However, we still have some problems. All of this, of course, as you can imagine, has altered the frequency response. In particular, the truncation is especially bad because this introduces a lot of high-frequency content, which are known as side lobes. And this is due to truncation and the discontinuities it brings with it. And the actual frequency response will probably look something like this. And remember our ideal low-pass filter frequency response from earlier. These are quite different. Again, we have a solution. What do you want to do after we've done all the truncation, shifting, and discretization? We want to multiply this impulse response by what's known a windowing function. And the windowing function, quite simply, is just a smoothing function to try and get rid of these discontinuities after truncation. You can see that will vastly improve the frequency response. Now, we will have many different choices when designing FIR filters. Firstly, we need to think of the sampling frequency. And this is oftentimes governed by the system we're going to be implementing this on. But ideally, if we could choose, we want to sample as fast as we can, because then we're not limited by a really low Nyquist frequency and so on. Secondly, the filter length is really important. So a longer filter, a longer impulse response will give us a more resolution in the frequency domain. Then, of course, we can define the frequency response in the filter type. So do you want a low pass, high pass, band pass, notch filter, and so on. The windowing function is quite important to choose as well. There's stuff like Hamming, Hanning, Blackman, and so on. Lots of different windowing functions we can choose from, and they all have different benefits in the time and frequency domain. But we're not only interested in the frequency response of a filter. Sometimes the signals of interest, our input signals, have really sensitive time domain information, and we don't want to distort that too much. So we might want to look at things such as rise time and overshoot and so on. So I've written a little program in C# that'll actually help you design different types of FIR filters. And you can find this in my Git repository under the Hades flight control system, and I'll leave a link in the description. Essentially, we have all the code here, and also the C code for implementation, and a bit of raw sensor data for you to test it out on. So we can actually use this to visualize the filter responses in the time domain. In the frequency domain, we can look at the window function frequency response and the window function time domain response. And you have all these different parameters down here that you can play with. For example, the sampling frequency, the filter length, how many samples we should shift the filter, and kind of the for different filter types, low pass, high pass, band pass, and band stop. We can plot the impulse and step response, and so on. And we can also choose the window function. So I really do suggest that you play around with this, because it's quite cool to see how different windowing functions have different effects on the filter responses. So we can play around with that here. Always click on Design Filter, and you can see that might have better stop band attenuation, less passband ripple, and so on. Yeah, so I strongly just encourage you to have a little play around with that, and it's quite good to see and get a kind of intuitive feel of what all of these parameters do and change. Another website I can recommend is this T-Filter, and this is basically an online FIR filter designer. You can specify your sampling frequency, the filter length you want, and you can kind of just add pass bands, stop bands, so you can make pretty arbitrary frequency responses for your filters. So we can use that, or use the tool I wrote to generate time domain coefficients, filter coefficients, and so on. But let's move over to actually implementing one of these filters. Before we can get started with writing actual code, we need to remind ourselves of what it actually is we need to implement. And in particular, the most important part of an FIR filter calculation is this convolution sum we have here. Now, again, it looks a bit daunting, but we can actually break it up down here. So essentially, all we want to do is compute the output, and we do that by convolving the impulse response with the input signal. And the impulse response is here, and we kind of shift the input signal via this formula. Now we can write this out and expand this sum, and maybe this looks a bit more appealing. And if you just look at this for a second and then just compare, then you can see that it actually isn't too hard. Here we can see that the impulse response goes from 0, 1, 2, 3, and so on to the length of the impulse response. But the more difficult part is actually that we have this input buffer, which changes all the time as we get new input samples, and we have to shift that. So we start with the first one, then we shift it by 1, shifted by 2, and we shift it essentially by the length of the impulse response. And this gets actually quite hard to do efficiently. The question is, how do we actually do this efficiently in code? Because this can really slow us down and make our filters really short or not work at all. So if we go the traditional method of just using normal linear arrays, I'll call them buffers from now on, the problem is we need to shift the input samples all the time, right? So let's say we start out with this array, we have a length 4 input buffer, we have 4 samples, we get a new sample, x of n plus 1, we need to move 3 of these, discard the last one, and put the new input sample at first place. So you can see here we need to make the jump from this to the jump here. We've shifted 3 samples and we've added in the new one. And as you can see, we spend a lot of time just shifting samples, and that's time wasted. So let's see if we can think of something better. The solution, and oftentimes in the DSP you will find this, is a circular buffer. Effectively, it's like a normal buffer, except we're keeping track with a pointer to the oldest sample. So let's say we have our length 4 array here. We have xn, xn minus 1, xn minus 2, xn minus 3. xn minus 3 is our oldest sample. And that's the one we want to replace as soon as we get a new input sample. And we also have a point that keeps track. So it'll point to the oldest sample. When we got a new sample, we put it in the array where the pointer was pointing to, and then we update the pointer. I'd suggest looking at this article, and I'll leave the link in the description, and this goes into far greater detail about circular buffers and their uses in digital signal processing. And I think it's a good read and explains the difference between linear buffering and circular buffering and why it's so useful. But let's get on with coding. So here's the FIR filter header file, and I just want to go through it quickly, but we'll actually be filling in the initialization and the update functions of the filter together in just a second. So I'm including this standard int.h because I'll be using types such as uint8_t. After that, we are defining the filter length, and you can just set that to any value and then change the filter coefficients. I'm defining a struct which contains the circular buffer, the index for the circular buffer, and the current filter output. Then we have 2 functions. One is the initialization function, which takes the pointer to the struct, which essentially clears the buffer, clears the output, resets the index. Then we have the main function, which is the update function. So it takes the struct to the pointer, it takes a current input sample, and it returns the filtered output. Okay, so let's see how we can fill in that initialization and the update function. So here we are in the firfilter.c file. You see I've included the header file we just talked about, and the first thing we see is actually an array of the filter length, and that will contain our impulse response. And then we'll look at that later, how to compute the impulse response. Then of course we have the initialization function, and I've written that for you because it's kind of boring. All I'm doing is running through the buffer, the whole buffer length, and just setting everything to 0. Then I'm resetting the buffer index, and I'm clearing the filter output. And you would do this when you create an instance of the object, and then you would pass that instance to this function, and that just clears everything for you. Alright, so now comes the main function, and this is going to be I think the most interesting bit, and so let's do that together. So we have the FIR filter update function, which takes the FIR struct and the latest input sample and returns the latest filtered output. So I've written some comments here of what needs to be done, and let's fill this in together. So the first thing we need to do is actually store the latest input sample in our circular buffer. So we can do that by accessing the struct, and then we need to put it in place where our buffer index is. Right? So we store the latest input sample where our circular buffer index is pointing to in the circular buffer. Then of course we need to increment the buffer index, because the next time we store a new sample we don't want it to be in the same place. Of course this is a circular buffer, and we need to make sure that we stay within bounds. So we can't have a buffer index which is longer than the FIR filter itself. So that's what we're going to check for next. And So if the buffer index is equal to the filter length, then of course we want to reset it to 0, because the next time we'll increment it to 1. Okay, so now comes the most interesting part. This is where we actually do the filtering and we compute a new output sample. So the first thing we need to do is set the current output to 0 again, because we're going to be using this, this register, this variable, to actually store the latest output sample. And we want to start from 0. Now, if you remember, this is the sum we need to implement. This is the actual convolution. So we can compute the latest output sample by following this. So essentially, we need to cycle through the impulse response from 0 to the length of the impulse response and multiply it by the shifted samples of the input buffer of our circular buffer. Okay? So essentially, all I'm doing now is implementing this sum. So let's do that. Of course, I need some sort of variable to keep track of where I am in this sum, and I'll just call that a sum index. And we started off at the FIR buffer index. Okay, then we have a loop where we're looping through the entire impulse response, right? So all I'm doing is implementing that mathematical formula. Okay, so the first thing I have to do is check if the index is all right. So if the index is still positive, so greater than 0, I would like to decrement the index. So I'll do that. Now, if it's 0, of course I can't decrement one further, then I actually need to shift the index. So now I've shifted the index, which we'll be using in this sum. Now I actually can get the impulse response and I can get the stored input sample from the circular buffer and then multiply them together and add it to the output. So I'm adding to the output the multiplication of the impulse response at my index n, and I'm timesing it with the input sample which was shifted. Okay, so to my output, which starts at 0, I'm adding the impulse response at n times by the shifted input sample. And again, all I'm doing is implementing this sum here. So the current output sample is the impulse response at an index times the circular buffer, which is the input buffer of a shifted index. This is all I'm implementing here. Okay, and that's pretty much all there is. This loop will run through, and after we've done with that, we have stored the filtered output in FIR out. So that's all we need to return. So all we had to do was store the latest sample, make sure we update the circular buffer index, then we compute the new output sample via convolution just by following this sum over here. And that's all this code is doing, and then we're returning the filtered output. And that's it. So now we can try and design a FIR filter and then test it out in real time. So as a global variable, I've made an FIR filter struct, and I've just called it low-pass filter accelerometer. We're just going to be using it just as a demonstration to filter one axis of the inertial measurement unit's accelerometer. Then, of course, we have to initialize the FIR filter, essentially just resetting the circular buffer, indices, and the output. And we do that just by calling the FIR filter underscore init and passing the low-pass filter accelerometer FIR filter struct by reference. So in a previous video on actually programming an STM32, I believe it was called STM32 firmware tutorial, we went through how we can actually write drivers for an accelerometer and gyroscope. And I would suggest you look at that video. I'll leave a link in the description. But essentially we had set up a DMA stream so that we can actually read the accelerometer data every time there's an interrupt. And this interrupt occurs 100 times per second, so at 100 Hertz, which is really good because we have a fixed sampling frequency, fixed sampling rate, and then we can always do our filtering as soon as we read something via DMA. And that's exactly what we're going to be doing here. So I have this callback every time the DMA stream reads a new sample, so 100 times per second. We read it, and once it's complete, we can then filter that accelerometer data. And so let's do that here. So this is actually where we would call the FIR filter update routine. So let me just type in FIR filter update. We pass the filter struct, and we pass the latest sample we read. So I'm just accessing this inertial measurement unit struct over here, which contains the accelerometer data. I'm just accessing the first value there, which is the x-axis. Okay, We would also like to transmit the raw and the filter data so we can plot the two and see if the filter is actually doing what it should be doing. And I'll just copy that over because it's not particularly exciting. You can see that in a previous video how that works. Essentially, I'm just creating a buffer to store the text in. I'm printing essentially two floating points, the raw data and the FIR filter data, and then I'm transmitting it via USB full speed. So now that we have all of our filter code written, it's time to actually design an FIR filter. And we'll do it using this program I wrote. So we have this raw accelerometer data, which will contain a lot of high frequency components that we don't really want. We want the accelerometer to be essentially correct or valid for the long term. So we want low frequency data to remain and high frequency data to be filtered out. And the way we do that is via a low pass filter. So the first thing we do is in the bottom here, we select the filter type, which is LP, which stands for low pass. We also said that we're sampling the accelerometer data at 100 Hertz. So we changed that here to 100. And filter length, essentially anything under 64 samples in filter length is probably fine, and the STM32 can handle it. But as soon as you go above that, it's going to have a real tough time keeping up. Just to be safe, I'm going to keep the filter length to 16 and shift it by 8 samples. So shift it exactly by half the filter length. So filter length, essentially you want to keep around 16 to 20. It's really hard to compute the filter for longer lengths. Now, we want the cutoff frequency. Essentially, we want it less than 50 Hertz because that's a Nyquist limit. I'm going to put it something around 10 Hertz. So the cutoff frequency will be 10 Hertz. Anything below 10 Hertz should have a DC gain of about 1, and anything above that should be attenuated, is what I'm basically saying here. Now, first of all, let's leave the window function as rectangular, and rectangular means we're not applying any windowing. So click on Design Filter, and now you can see the filter response in the time domain. We can see the window function in the time domain, the filter in the frequency domain, and the window function in the frequency domain. As you can see here, we have these nasty side lobes because we aren't doing any windowing, and the filter response isn't too ideal, right? At about 10 Hertz, we only have about -6 or -5 dB of reduction. So the way we can improve that is by actually doing the windowing, what we talked about earlier, and a really good window to always use is pretty much the Hamming window is a pretty good window. So we click on Design Filter again. You can see our stop band attenuation is improved. We've reduced the amplitude of these ripples or these side lobes, and I think that should pretty much do us for now. So remember, sampling frequency, filter length, the amount of samples we shift, the cutoff frequency here, window function, and we want the filter type of low pass. Okay, so once we've done that, we can click on File, Export Filter Coefficients, and I'm just going to save it as a text file. There we go. And it says it has written it to a file. We can actually open it. And you can see here, this is the file it generates. So it'll tell you what the filter order was, the sampling frequency, and so on. And I've already made it so it converts it to a C array, and we just copy that over into our code, which is over here, and we just replace the array with these filter coefficients, and it's as easy as that. So now that we have all the filter coefficients and the filter code written, all that's left to do is essentially launch the program, upload it to the STM32, and we can do that by clicking this green arrow up here. Click on that. It'll then hopefully build, and then use via serial wire debug, upload it to the STM32 and the little brain board. This is a really cool program that I'll be using to visualize the data that's being streamed via USB, and it's called Serial Oscilloscope, and you can find it on this website, x-io.co.uk, and you can download it down here. So now I have the serial oscilloscope running, and the STM32 is logging data via USB. So the first first column here is the raw data from the accelerometer x-axis, and the second column here is the filtered data via our FIR filter. And we can actually visualize this here. So I have the board in my one hand, and if I just rotate, and then we can see the values change, you can see the red curve is the raw data, so quite noisy, lots of high frequency noise, and the green curve is the filtered data. So I'm just doing very slow movements, and you can just see how the low frequency curve follows it very nicely, which is what we want. But all the high frequency data is kind of filtered out, which is pretty good. So if I just move it like that, you can see it follows it quite nicely. If I just let it stationary, another important point is that the DC gain is the same. So I'm not moving it, and we want the values to have the same mean, which they do, so that's good. But as you see, if I start increasing the frequency of oscillation, you can see that actually the green curve lags behind the red curve. So the filter data lags behind the raw data. And this, of course, can be problematic. And this depends on your cutoff frequency and how much filtering you're applying. Because the more you filter the signal, the more delay you're going to introduce into the signal. And this is exactly what we're seeing here. So if I speed it up even more, you can see the high frequency information is really filtered out, which is what we set our filter to do. So it works really well up to the cutoff frequency, and as soon as we increase the frequency of the data, then of course we will lag and reduce the amplitude. But yeah, so this is a really nice visualization of our FIR filter actually working.